friend. You should check us out. And you can follow me on Twitter at rsandor, it's my Twitter handle. So what we're going to talk about today is something that's becoming increasingly important as for JavaScript developers, and that's memory management in the heap and how garbage collection works. So we're going to investigate like what the heap is for those who don't know. For those that do, sorry, it might be a little boring. And we'll go into different types of garbage collection that occurs in JavaScript engines, and then we'll see how we can actually use the information to develop better applications. So if you have a process that's running on your computer, it has a specific amount of memory that's given to it by the operating system. And this memory is segmented into two sections. And one is called the stack, and this is for things like return values and local variables that are being used in the thread of execution. And the other more important part to our talk is the heap. And the heap is used for any sort of dynamic memory allocation. So if you need to initialize an array of a certain size in C at runtime, you would put it into the heap. You wouldn't be able to do that statically on the stack. So the memory lifecycle for a traditional application boils down to 3 steps. The first step is to actually allocate the memory that you need to use in the heap. To use it, of course, write and read values from it. And then finally, you need to, and you're responsible for freeing that memory lest you run out of available heap memory. So this is just a basic C example. We can see that we have a couple of variables, C and str, that are actually existing on the stack, and those are going to be in like the activation record. And then below that, we actually allocate using a function called malloc. And this is just like the traditional way you would do it. You go in, you say, I need a string that's going to be 100 characters long. You would do things with it, and then when you were done with that string, you'd actually have to like call free. So in like older systems languages, this is exactly how you would do it, but not so much in modern languages. So most interpreted languages now deal with this for you. Most interpreted languages even in the past deal with this for you. And the idea is that it's kind of a pain to have to do this every time that you need any sort of dynamic memory in your application. So most of the time, it's just going to handle all of these things for you. But as we'll see, allocation in JavaScript happens all over the place. Anytime you use new to instantiate a new object, you're actually allocating into the heap at the base level in the engine. Any implicit objects like curly braces, brackets, strings, those are all going to be going into the heap. Any sort of factory methods like document.createElement, we're writing memory, allocating and writing memory into the heap. And it's really pretty much anything that you're doing in JavaScript is going to be touching the heap in some way. Even the very act of interpreting the program and parsing it, you're going to be doing a lot of heap work. So here's a little example. We look at this new string. That's obviously, we're making something new. And even back in the days of like C++, you use new to allocate heap memory. This next bit here, all of these are pretty interesting. So the first one, you just have an implicit allocation of a string. The second one, you actually have an object allocation. You have a key and a value, which are both used as strings, which are going to be allocating into the heap. So you're actually getting 3 things going into the heap. The array, 1, 2, and neat, obviously, the array and the string is, but then those numbers are acting like objects. You have methods on them like toFixed and toString and stuff like that. So all of these things that are happening here are going to be in the heap. And then the last one is actually pretty funny because that function exists in the heap as an object. And then when it's executed, you actually get the function in the heap and an execution scope for the lexical scoping for that function that exists in the heap. And then even the OMG that's being returned is going to be in the heap. So as you can see, like everything is just you're really creating a lot of memory. The interpreter and the engine's going to be creating a lot of memory, even for a very simple application. So there's lots of heap, and you're using it all of the time. And the problem is that memory that you use in the heap isn't necessarily going to be useful for the lifetime of the program. So that means that you have a lot of garbage. And what I mean by that is memory that's in the heap that you don't need. So there's a method called garbage collection that's used for most interpreted languages. It essentially removes the programmer from having to do the traditional life cycle where you have to allocate, use, and then free. It automates the entire reclamation process from the heap. And it's been around for a long time. Like it shows down at the bottom, it was actually invented in 1959 for Lisp, which, if you have any experience with Lisp, is similar functional type style language, which can really use this kind of like dynamic allocation, deallocation, without having to like directly address the system memory. It is not magic, meaning it's not going to do everything for you. It's not going to be like you never have to worry about memory management again, and that's exactly why I'm giving this talk, is because I used to think of GC as magic, and I realized that having an understanding of it can be helpful, especially when things get a little out of hand. So to understand why it's not magic, you have to look at what the various definitions of garbage are. There's the first type, which is semantic garbage, which means that memory is no longer used. And another type called syntactic, which means that the memory is no longer actually reachable. And what we mean by reachable is reachable from the global state or the root set of the execution that you're doing with this program. Just a small side note, syntactic is actually a strict subset of semantic, meaning that if it's not reachable, it's no longer used, but it doesn't necessarily mean it's no longer used if it's still reachable. So semantic garbage collection would be great, and it would be magic, because any memory that you've used that would no longer be used by the program would automatically be freed by a semantic garbage collector. It would completely eliminate you from the process to let you worry about the problems that you're working on as opposed to actually managing the memory. But it's undecidable, meaning that you can't compute it. It's like the halting problem. And there's actually a theorem, I can't remember what it is exactly, but it has to do with any non-trivial questions about a program itself tend to be undecidable, and this falls into this category. Syntactic garbage collection, however, is decidable, and it means something is no longer reachable from the global state or the root set of the program. There's a lot of different ways to do syntactic garbage collection, and the only problem with it, and the reason why we're talking here, is because it doesn't actually eliminate you from the picture. There are still things that you have to do in order to let it do its job correctly. So the idea is, again, you want to determine what things in the heap, all of those strings and all of those objects and all of those various things that you're putting in the heap, which of them are actually reachable. And the ones that are not, you want to be able to automatically free those. There's a process that's running in the background in the engine that's just automatically going to get rid of that memory and keep your heap nice and small. And the reason why there's many actual methods to syntactic garbage collection is because reachable can actually be decided in multiple ways. So the first basic example of a garbage collecting system is called reference counting. And in reference counting, what you do is you keep, for each object that's in that heap, you keep a count of how many other objects in that heap are keeping a reference to it. Then, when an object reaches a reference count of 0, means it's no longer reachable by any other objects. And mind you, like the global scope that you're using in JavaScript or any function scope, these are also objects that can be referenced back and forth. When it reaches 0, then it's automatically freed. If you're familiar with like iOS programming or anything like that, you actually, like at least back in the day, I guess it's a little more automated now, you use a scheme very similar to this for reference counting between objects as you're doing things, and it allows it to be more structured instead of the kind of free-for-all that you would get from just straight, C. So here's a little example of how it works. So if you look at line 2, you have a variable A, and it has one reference, and that's the global scope. Then we're making an anonymous function below there, and inside there we're creating something called B. B at line 6 has one reference, and then we actually reference it from the object A, so now it has 2 references. When we get down to C, C has one reference to the global scope, and then the function exits. When the function exits, the scope goes away, so C no longer has any references, so it gets swept away. And B only has 1 because of line 7, because we were referencing it. So after that function exits, B still exists in the heap and it won't be freed. And then at the very bottom, we're actually going to null out that reference. And at that point, B doesn't have any references, therefore it will also get collected. So reference counting is actually pretty simple. Like you just keep a tally. And as the interpreter goes along, it can know when something's being referenced or something's not being referenced, and just go up and down in the reference count. When it reaches 0, it's done. It's actually used by older engines. Like I know the JScript engines for IE6 and IE7 use it. I've heard that IE8 might use it, but I'm not actually 100% sure on that, to be honest. But it does have a few issues, and namely circular references. So if we were to implement this reference counting garbage collection system for JavaScript very naively and just keep the reference counts, this would actually cause what's called a memory leak, meaning memory that's not reachable but it's not being collected. So in this function leak, we're creating two objects. Again, they both have reference to the global scope. And then we're setting a reference to each of the objects to each other. And when we do that, now they each have two reference count. The function leak exits, the scope of the function goes away, so now they're both down to 1. But as you'll note, there's no actual way that you can get at A or B because they were scoped within that function, yet they still both have a reference count of 1. So they'll just persist for the rest of the execution. Now, this doesn't happen in modern browsers, as we'll see in a little bit, but this is the very definition of a circular reference right here. A little bit more of a involved example here, we have an onload method for the window, like using old-style inventing. And we create this whole closure that has all of these elements in there, and then inside of that closure, we create another onClick. Now, the interesting part about it is because of lexical scoping, remember, each of your scopes is an object that exists in the heap. So now we have a pointer to the enclosed onload inside the onClick, and variables like n and s can't be removed as long as the onClick exists. Like if you clear the onClick, it should go away. Another problem with that too is that this actually goes between in older browsers, this goes between two memory spaces, which reference counting the garbage collection is independent for those memory spaces, and that's the DOM and the JavaScript memory spaces. And so your reference count garbage collection system can actually, in these older systems, deal with that, and it will cause a memory leak situation where if you're not eventing correctly, or if you're trying to connect DOM elements to actual JavaScript objects, you're going to create a memory leak. And this is something that still happens in stuff like IE6, IE7. If you have to work on legacy browser programs that work on legacy browsers, this is still something you have to worry about, so you have to be careful. There's, I think, even a Microsoft development article from 2006 that talks about not using closures as much as possible just to avoid this, which just doesn't make a lot of sense to me, but apparently they thought that was the best way to do it. So the problem here, though, is that even if you can find these basic circular references, you'll still have situations like this, where you have a very complicated graph of objects in the heap that are all referencing each other and not getting down in count. And so eventually it comes to a point where you have to look at the entire heap and really understand what's going on. So that's what we do with mark and sweep. And it's a really simple concept. The engine does look at the entire heap when it's trying to determine what needs to be freed and what doesn't need to be freed. So essentially what it does is starts at the root set, or your global scope, looks at all of the variables that you have there, and does a tree traversal going along all of these reference points. And each time it reaches something, it marks it and says, okay, this can be reached, keep this around. Then after it's done doing the entire traversal of that tree in your global scope, it just does a linear sweep across the heap memory, looking for any objects that aren't marked and removing them. So that way you're getting full coverage of the heap, and the idea of the circular references isn't going to be a problem. So it's kind of slow, but it can be made really fast. There's modern approaches. There's many different ways of doing it and many different add-ons you can do. Like you might come across articles every once in a while if you're doing any sort of research into it that say, Google Chrome V8 engine implements incremental garbage collection, things of that nature. All of those sorts of things are just add-ons to the basic mark and sweep algorithm, and all modern JS engines use it. So you don't have to worry about any of that stuff. As an example, in leak again, we do the exact same thing. We set up the circular reference, but after leak executes, eventually the garbage collector will run, and A and B aren't reachable from the global scope anymore. So it's because we're not just looking at how many references they have, they'll do the whole tree traversal, and in this basic program, the only thing that exists in the global scope is leak. That's not a built-in. It'll find leak, it'll realize that that's good, so it keeps leak around, but then it doesn't find A or B, so it never gets marked. And then when the sweep occurs, it goes to the A and B objects inside of the heap, and since they're not flagged, they get removed. So it completely gets around all of that. So, in essence, you usually don't have to worry about garbage collection nowadays. In modern browsers, garbage collection is really good and really sophisticated. You used to have problems like I said, back in the early IE days, well, early relatively, like IE6, IE7. Circular references aren't a problem because mark and sweep looks at the entire heap. You can't actually force JavaScript to do a garbage collection run. It's going to do it when it wants to do it. Like, you can't do it from JavaScript. There's various tools that will allow you in browsers to just like force a garbage collect to see how things are working, but you can't actually do it from code. So why are we talking about this if it's completely good and completely easy? And there's a really good reason. That's memory bloat. So what will happen is if you're not mindful about clearing references and you're not mindful about how the garbage collector works, then your program's heap memory will grow and grow and grow and grow. And in like Chrome, you can easily get up to 1 gigabyte of heap memory because these pages stick around for a while nowadays. It's not like we're refreshing the page every time. So again, pages can be active for a long time. So at Fastly, one of the first things I did was create a analytics dashboard, which just had like real-time analytics that were coming across in our network. And we found out that customers were leaving it open 24 hours a day, 7 days a week. That means that even if I have the tiniest leak, after a month, they could easily have 1 gigabyte of heap memory or more than 1 gigabyte of heap memory just to run that single page because things aren't being freed. When you start to use too much heap memory, your computer slows down. So because you only have a limited amount of actual memory, you'll have to go into what's called paging, where it writes the memory to the disk and then loads from the disk onto the main memory. And if you know anything about hard drives, even SSDs, they're orders and orders of magnitude slower than main system memory. So having too much bloat can actually cause real side effects for your users on their own PC. So our goal here is to actually try to keep in our programs and in our web pages that have to run continuously for a long time, our goal is to keep the heap as small as possible. And the way that we do that is by nulling out references. It seems pretty an easy thing. Of course, you just null out your references. And another thing, too, is understanding what the delete keyword does. Because some people seem to confuse delete from actually like nulling out references, but we'll get into that. So here's a really quick example. Say you have a class, and it's some sort of node wrapper, and it's supposed to be helping you do things with DOM nodes. And in the constructor up there, we see that we're grabbing an ID, an element by an ID from the DOM, and assigning it to a local variable. So now we have this like cross-space JavaScript to DOM memory heap connection. Then down below, you'll see that I've created a method called destroy. Now, destroy isn't anything special in JavaScript, of course, but what this is illustrating here is that you want to give yourself a way to remember that you need to free these references. And one way that you can do that is by just using really basic conventions to remind yourself. If I have an object, it should always have a destroy. Even if it's holding no references, you should maybe just keep it there to remind yourself, because there are some objects that just have references, tons and tons of references. So below that, we just create the node wrapper, look for MC hammer in the DOM, and then do some stuff with N, and then afterwards we call the destroy, which automatically cleans up all of those references. So if we didn't do that, it's a possibility that we could be removing that element from the DOM. And this node wrapper could actually still exist somewhere in one of our views or something like that. And then that DOM element's never going to get actually garbage collected because there's still a reference to it inside this class. So by calling destroy, we're removing that reference and making sure that it's no longer reachable. And when it's no longer reachable, it just gets removed. Another example, say you're going to build a very old school style like linked list. You have a left, a right, and a value. And then you do your rest of your implementation, you get to the point where you get to remove. And this is where you're just removing an item from the list and then taking the two items that are adjacent to it and connecting each other. And as you can see in like 13 and 14, we're just doing the connection. And at that point, you're actually done, because as far as the terms of the whole list object, if you have like a root, this item's been removed. You don't have to worry about it anymore. But there could be the case where, say you take the right element, you bring it out, and you actually end up destroying that element. You get rid of any references to it. In another way, like there's maybe like a destroy method or something like that. Well, this one will still have references to left and right, so that might never be called. And if it's never removed, this like data structures especially are used, and usually very tight loops are used a lot. It could actually lead to a considerable amount of bloat just because you're not removing your references. So even over convention, you have to be careful about it and really think about when you need to get rid of references, even if it's code that might not necessarily be directly convention style remove or take care of this item from the heap. Some notes on delete. So delete, it should only be used to remove properties. I didn't know this immediately when I started programming in JavaScript. I actually didn't know what delete did because I don't like to read. So and its behavior is actually very fickle. It depends on what are called execution contexts and methods of assignment. You can't delete anything like built-ins, like you can't delete the array class. You can't even delete the .length property on array, because something that happens is in the interpreter, what it will do is it will set a flag called don't delete on various types of variables. Anytime you do a var x equals 20, that is called a variable declaration, and it automatically sets a do not delete flag. So if you try to get rid of it with don't delete, say you have like a closure and it has a bunch of references in there and you try to go delete this reference, if you declared it with var, it won't get rid of it. That's why you should always really kind of use it for things like removing properties on objects, which is what it's built for, and try not to rely on it for like dereferencing. Dereferencing should always be, assign null to whatever your reference was. There's a really, really good, really long, mind-bending article about exactly how delete works. I don't know if you can really read that down there, but if you want to read it, just ask me about it later, and I'll definitely get you the link. DOM elements. So anytime you're doing anything big with the DOM, it can cause a lot of bloat if you don't get rid of things. I've heard horror stories of people talking about how they were trying to keep entire DOM trees chilling out because they thought it would be faster. But this happens over and over, and you have too much memory. You can actually be slower because you start paging. You just page thrashing. So whenever you're done with the DOM element, our engines are fast enough nowadays. Just get rid of your DOM elements, dereference them, get rid of everything. Use like jQuery.remove to get rid of all of the events. You want to get rid of all of the references to them so that they can be cleaned up, because you don't really need to keep DOM elements around anymore, in my opinion, unless you're doing something really, really massive. You can usually regenerate that code over and over again and not really see any hiccups in your user experience on the front end. Finally, like events. So if you're not eventing, especially on the front end, if you're not eventing correctly, if you're not using things like delegates, you can create a lot of bloat, especially if it's a page that creates items over and over again, or maybe like imagine like Twitter, where it, over time it just accumulates more and more messages, and each one of those like individual messages has all of these different actions. If you're not actually using event delegation, this can cause a massive amount of bloat and a massive amount of headache. So just a great reason to use delegation is just to keep your memory footprint small. In systems like Backbone, where you have custom eventing and you're connecting all of your models and views and controllers together through all these wonderful events, you got to be careful, because you got to make sure that you unbind those things if they're no longer usable. If you have a view that's going to be falling out or being destroyed, you have to unhook it from the model. It should no longer respond, or unhook it from whatever you're hooking it into. This is particularly annoying too if you're using CoffeeScript, which is I do a lot, and like fat arrow binding the scope, because now not only are you binding some basic callback to your event, you're binding a callback that is actually bound to a scope of the object. And so now you have this entire object that is referenced, and all the way through this callback, and if that callback never gets unbound, then this entire object, which could be huge, never gets collected by the garbage collector. And so it can also cause some really weird actions to occur, where if you're not unbinding your events appropriately, you're going to be calling a callback on an object that references things that don't exist anymore, causing errors. So just, if you have a convention that you follow for trying to help clean up the memory, just make sure you include events. Like, think about events when you're doing that. So the unfortunate part is that we all work on big, large projects with lots of developers who don't understand exactly how process memory works, or might not really think that it's a big deal. And that means that no matter how much I sit here on my soapbox and tell you that you need to be careful about how you manage your memory, you're going to have memory leaks in your applications, single-page applications, things of that nature. So that's why you really got to look at some of the amazing tools. Like Google Chrome has some great things. You can take snapshots of the heat. You can compare two different snapshots over time and see the differences between them. You can watch memory usage over time and see when garbage collection cycles run. You can force garbage collection from there to make sure that you're not growing too much. Other browsers, I think Firebug has similar tools, and then older browsers, there's like third-party like applications you can use to inspect the heap and things of that nature. And like I said, it can be really impractical, especially if you have like a dev team that's large, to really try to be super preventative about this. There'll eventually come a point when a page gets slow, and it's because of memory bloat. So just be mindful that there are ways for you to find and fix these things. And that's my talk. So thank you very much for inviting me here to speak about it. Yeah, so I kind of know why that is. So garbage collection so I've also found this where you'll have a page running and then you'll try to get like refresh it, but that memory just doesn't go away. So you can be really lazy, and like some of the browser implementations are very lazy about when they get rid of memory and when they don't. There's also a possibility that you just have a memory leak in your application that's causing it to think that these might still be needed because you're still on the same page. So there's a good chance that you could have a leak situation occurring. Right. Which is like the best way to do that is to actually close the browser window, and then you'll see all that memory disappear. Well, that's good. Thank you. So they say. The browser developers say a lot of things.
I remember back in the 90s, programming in Java, and the advice was not like the references. And then the JVM got smarter, and the extra reference to the variable to null out later on actually stopped it being garbage collected. I made it worse. At what point are the VM manufacturers or the VM developers actually harmed by manual attempt optimization?
So one of the things is that even over the last few years, the garbage collection systems in JavaScript have just gotten massively more advanced. Like I said, you don't even really worry about circular references and stuff like that anymore. I think there will come a point where it will be smart, but I'm not sure when that point will come. And I imagine that nulling out references for now would be good. I'm trying to think of like what they could possibly do to make that even easier. Because like anytime you're exiting a function scope, like so you have local variables in your function scope, like I was saying, anytime that scope pops off, those references should be gone. Nothing should be referencing them. The problem is that when you have a really complex system like a backbone app or something like that, that's like thousands and thousands of lines, that connections in between things can get really hard, so still clearing out the references seems like a good idea. And again, like you can just wait. You can wait until your site gets slow and try to find them and just be really lazy about it. I mean, that's what I did initially. Now I'm a little more like crazy about clearing out my references, so yeah.
Do JavaScript garbage collection engines have generational?
Yes. So Google Chrome actually has generational, and I'm not sure about I did a bit of research on that. Yeah, generational is there, and what generational means for anybody who doesn't know is that they split up the heap memory into older objects and newer objects, so it makes it faster to actually do a GC run. Like, so as you're going through the heap and doing the mark and sweep, you'll like segment them in a way that makes it easy to understand that these ones might not be taken immediately. So let's look at them less periodically or less often as we look at the new things that are happening. Well, the first thing that you got to look at is just if you're worried about it initially, just look at like the process manager in like Windows or the activity monitor in Mac and look at that kind of thing and see if you're actually bloating over time. And I have a link that I can give you. I don't have it right on me, but there's a suite of tools that can help with that. So.
When you've got libraries like Knockout, you're kind of farming out serious dominant information to what extent are they kind of thinking about garbage collection? There are some libraries that are doing lots of this for you, or other ones that
Right. So for the most part, you can't expect anybody to do this correctly because, one of my major viewpoints is that as programmers, we're just going to screw things up all the time. and especially when you have a large collection of programmers working on an open source project or something like that. I think that it's becoming more and more a topic of interest to the plugin developers, so I wouldn't be surprised if Knockout was making, especially with all the kind of like MVVC crazy they're doing with DOM connection, that they would be paying a lot of attention to that sort of thing to make sure that they don't have just dangling references, because it doesn't help your framework if your framework makes all of the pages that use it slow. So I imagine that they would be, but it really depends on it. You'd have to like maybe dig into some of the code and see what they're doing and things of that nature. No, Backbone doesn't do crap, really. It just gives you a list of things, to basic methods, and doesn't do much. So Backbone, what it does is it gives direct exposure on views to like the jQuery remove or whatever remove that you're using, and that's good for taking care of DOM elements. But yeah, it's the Wild West with Backbone. You've gotta do it yourself and make sure that you're keeping. All the app that I build at Fastly is all in Backbone, and sometimes stuff like that is just like really crazy. Sprout Core. If anybody's familiar with that, Sprout Core actually has a flag you can set on objects to tell them to be like removed and things of that nature. I'm not exactly sure how that works because I don't use Sprout Core too much, but most of the major frameworks are starting to recognize that this is an issue and providing ways to actually get in there and do things. Oh, okay. Yeah. So, well, okay, so like on an individual object basis, it's not usually very feasible to do that. But like if you look at the heap snapshots in the Chrome tools, whenever you see something growing, like you'll have a very large delta if you compare the two, it'll actually give you references to the very objects that are causing this to be a problem. So like if it is a problem, you'll be able to find it very quickly. So. Mm-hmm. Closures. Like you create your scope with closures for the most part, like a using with sort of thing. The idea is that like if you want to keep things that are going to be cleaned up, like say you're doing some sort of algorithm to optimize something and you need to have a lot of metadata about this large array of objects, stick it in a closure, run that closure, and then any of your local variables will automatically be dereferenced and out as long as you don't reference to anything outside of that closure, and everything will be cleaned up. That's why it's in the kind of the nice feature of the functional aspect of JavaScript that allows you to just create scopes on the fly as you need them to separate out code. Is that about it? Thank you guys.